Okay, good morning, good afternoon, good evening, good night, depending on when you're watching this video. So we're going to work through exercise number 2 on slide 38 of lecture set number 7. All right, so here we have the following simple random sample gives the number of genes that show evidence of positive selection from humans that were compared with their chimpanzee orthologs. A normal probability plot for the sample is shown below. Compute a 95% confidence interval from you. All right, so the first thing we do, assumption check. Okay, so 1 SRS. This is fine because we're told that the population is, or we're told that we have a simple random sample. 2 X bar is normal. Okay, in this case, our sample size is only 14. You can see this because there's 14 observations in the table. We don't have enough information, or we don't have any information about the distribution of the population. We don't have enough observations to use the central limit theorem. So we are given a normal probability plot in this case, which is what we would build ourselves if we had to in this circumstance. And you can see that the values here appear to be linear with the quantiles of the normal distribution. There's certainly all the values are well within the bands. Maybe the 14th observation is outlying a bit, but it's still relatively close to the line. So we can assume normality given the QQ plot or the normal probability plot. Okay, so given linearity in normal probability plot. All right, and then the third assumption is sigma known, and that is not true, right? We don't have any population information at all. Okay, so we want to build a 95% CI. So the first thing that we do, we write down alpha is 1 minus 0.95, which is 0.05. So then we have T alpha over 2 n minus 1 is T 0.05 divided by 2, comma 14 minus 1. So this is T 0.025, 13. We go to our T table, 0.025, 13. So that gives us a T value of 2.160. This value here is 2.160. Okay, so then we come back here. Now we have X bar plus or minus T alpha over 2 n minus 1, which is multiplied by S divided by the square root of n. Okay, so this is going to be, well, what do we need actually in this case? So this is the interval we want to build. We don't have X bar, we don't have S, so we got to compute them, right? So make a little sidebar here. X bar is the sum from I equals 1 to n of xi divided by n. So we're going to add all the values up in our data set and divide by n. If we do that, we should have 1106 divided by 14, and that gives us 79. Kind of cool, worked out exactly. What about S? Okay, well, S we can find using the computing formula. So let's do the variance first, and then we'll just take the square root. It's a little bit cleaner. So we have the sum I equals 1 to n xi squared minus the sum I equals 1 to n xi all squared divided by n over n minus 1. Okay, so you can see how we're drawing on our previous techniques, right? We're using formulas that we established earlier in the course. These are all examples from the descriptive statistical unit. Okay, so first thing, we're squaring every value of x and we're adding them together. So if we square every value of x and add it together, we should have 104,134, right? And then that's going to be minus 1,106 squared over 14. And this thing is going to be over 14 minus 1. Okay. All right, so we go through that process. This gives us 16,760 divided by 13. And that gives us 1,289.231. Okay, so therefore S is the square root of 1,289.213, which is 35.906. Okay. So now we can come back to our interval. We're going to have 79 plus or minus 2.160 multiplied by 35.906 divided by the square root of 14. That gives us 79 plus or minus 20.73 or 728. Okay, so we add and subtract this. We have 59.272, or sorry, 58.272 to 99.728. All right, and then we can say we are 95% confident that the mean number of genes that show evidence of positive selection is between 58.272 and 99.728. Okay. As always, if you have any other questions, please let me know.